Isomers R and S are shown. So for 10.4 we've got two isomers. They look fairly similar, except in this case the carbonyl groups, the C double bond O groups, are at carbons number 2 and 5, whereas here they're at 3 and 4. And that's going to be critical in a minute. Although the carbon-13 spectra of R and S both show the same number of peaks, the spectra can be used to distinguish between the isomers, give the number of peaks and justify how we can use the spectra to determine between them. Well, the number of peaks, they're both completely symmetrical. Okay, we've got a CH3 at either end, they'll give one peak, they're in the same environment. We've got a CO at carbons 2 and 5, they'll give a second environment, and the CH2s at 3 and 4 will give a third carbon environment. So that's got 3 peaks. It says they've both got the same number of peaks, so this should have 3 also. Let's check. 2 CH3s at either end, yes, that's one peak, one carbon environment, one peak. CH2 is next at carbons 2 and 5, that's the second peak, and then the 2 COs at 3 and 4. They're both the third peak, so they've both got 3 peaks. Now, how can we use that? How can we use the data to determine between them? Well, we've now got to look at the shift pattern. So we've got to look at the delta shift, the shift number, the shift value. So let's have a look at the shift value for a carbon bonded to a CO. You can see that's a bold carbon, so that any carbons bonded to a CO have a shift value between 20 and 50. So how many carbons are bonded to a C with an O? 1, 2, 3, 4. All 4 of those carbons are bonded to a C with an O. Now 2 of them are of the same. We've got a peak there from the CH3s and a peak there from the CH2s. So we've only got 2 peaks out of the 4, but both of those peaks will be in the range 20 to 50, because all of those carbons, the 2 methyl groups, which are equivalent and have got carbons in the same environment, give 1 peak, and both of those are bonded to a C with an O, so we'll be in this range. And the 2 CH2s will give a single peak, they're equivalent, and they will give a peak in this range as well, because they're bonded to a CO. So this one gives 2 peaks in the range 20 to 50, whereas this one only has the 2 CH2s bonded to COs. So these 2 CH2s, which form a single peak because they've got carbons in the same environment, that single peak there from those 2 will be in the 20 to 50, but this CH3 is not in the 20 to 50 range. It only has 1 peak. S only has 1 peak in the 20 to 50 range. The hydrogen spectra of R and S both show the same number of peaks, but again this can be used. So let's have a look. How many peaks will there be? How many hydrogen environments? 1, 2 for this one. So we've got CH3, 3 H's there and 3 H's there. That's one environment. CH2, CH2, these have second environment. So this will have an integration value of 6. These will have an integration value of 4. These ones, I've got 2 CH3s, that's 1 peak, and I've got 2 CH2s equivalent with the H2s there. That will give a second peak, and I've got an integration pattern 6 to 4 again. So the number of peaks are 2. It's going to give 2 peaks because I've got 2 different hydrogen environments in both, and with an integration pattern of 6 to 4 in both cases. So that's not going to help me. So maybe I can look at the splitting pattern. So let's have a look at the splitting pattern. That CH3 there and that CH3 there is bonded to a C with no H's. So that's a singlet. That's going to give a singlet. This CH2 is bonded this way to a CH2. So that's going to give to this split into a triplet by those 2 H's. So that's going to give a singlet and a triplet. So R gives a singlet and a triplet. Whereas S gives that CH3 is going to be split by a CH2 into a triplet, but this CH2 is going to be split, the H's are going to be split into a quartet, so that's going to give a triplet and a quartet. And so it's the splitting patterns that are going to be able to determine which isomer is which.